Hi everyone, welcome to this Agile Oxfordshire Meetup where we're going to talk about Agile and hardware, specifically when Agile gets physical. And welcome Katherine, welcome Kathy. I'm really happy to have you two present to us today. And without any further ado, I'll just pass it over to you and then you can introduce yourself and get us going on this wonderful topic.
Okay, thank you. All right, so I'm just going to quickly introduce myself and then Kathy, and then we'll talk about some of the things we're going to try to cover today. So Kathy and I both came out of HP. That is where we met. That's where I grew up as a product developer. Started out as firmware engineer and firmware engineering manager, and then eventually just kind of worked my way into a position where I helped other teams get their products out. Along the way, I encountered the ideas that became Agile. And that is also where I encountered Kathy, because Kathy was also very interested in that. And then also ideas around lean. And the lean ideas have also had a lot of influence on Agile, even though that's not always, not always obvious. So back in about 2010, I was working as an external consultant. I had left HP in 2005. And in 2010, I started working with 4 different companies simultaneously. 2 of those companies were in the United States, a company called Steelcase that makes office furniture, and Whirlpool that makes appliances like washers and dryers and things like that. And then 2 companies in Denmark, one Novozymes that makes enzymes, and then Novo Nordisk, which is a pharma company focused on diabetes treatments. At Novo Nordisk, the specific ask was, can we adapt Scrum to advanced research? They had an advanced research lab focused on the biochemical mechanisms behind diabetes complications. And they wanted to know, could we use Scrum to manage that process? Now, I had been away from Agile for a while at that point, so I invited Kathy to join me on that project. And so Kathy and I spent some time in Copenhagen working with our friends at Novo Nordisk. And we learned some things along the way about, well, we can't exactly use Scrum. There were things about Scrum that didn't necessarily work all that well, but definitely a lot of the Agile principles applied. And that when we focused and drew back to the Agile principles, that there was a lot that we could learn. Now, what happened among those 4 companies is we would take the learnings from Novo Nordisk and I would feed them into Steelcase, and then take the learnings from Steelcase and feed that back into Whirlpool, and then Novozymes, and then Novo Nordisk, and kind of all around until at the end of this process, this thing had emerged called the Rapid Learning Cycles Framework. And since about 2013 or so, the focus of my work has been introducing companies to the Rapid Learning Cycles Framework, which is best described as an adaptation of Agile principles for the earliest phases of product development, specifically physical product development. So I work with hardware companies. I work with solar panels, and I work big heavy forklifts, and hearing aids, and pacemakers, and things that are very tangible, physical products, right? We're going to talk a little bit about what we have to do to apply those principles in that physical space in the earliest stages of product development. And then recently, I had started collaborating again with Kathy, specifically on what happens when an Agile software team interacts with a hardware development team. And as you know, many, many products these days are actually bundles of hardware and software. And so Kathy and I have been working out, what does that integration look like when it's working well? Again, kind of pulling back to those Agile principles and thinking, well, how can we apply the Agile principles to the specific problem? So the work that we're going to share with you today is fairly new. In fact, we've never presented it like this before. You are the very first ones to see this. And we are working on a book that is going to be coming out later this year, specifically on adapting Agile for the physical product world. So I'm very happy that David Michelle invited us to deliver this presentation, because it's really going to give us a good opportunity to air out some of these ideas. We're hoping to get feedback. We're hoping to get feedback now. We've got our LinkedIn profile on the page, so you can connect with us afterwards to continue the dialogue. And we're really, really hoping to do that. So Kathy, would you like to introduce yourself?
All right, my name is Kathy Iberle, and I also started at Hewlett-Packard. I worked in a variety of different organizations there. I worked in electronic instruments and medical products, and 2 different printer divisions, and a couple of other things, including e-services for a while. And I started as a software developer. I started doing things that were precursors to Agile in the 1990s, and then waterfall, so back and forth between Agile and waterfall. And I first encountered Katherine on a project in, I believe, 1999 or 2000, where she was introducing evolutionary delivery, which is a form of Agile, to a group I was working with. So I ended up becoming a technical expert on process improvement and a test lab manager. So I was doing test strategy and helping people figure out what would make it easier or faster to develop the products that they were working on. And I finished up my career in Boise, Idaho, and left HP in 2012 to become a consultant. And the first job I had as a consultant was working with Katherine and some of the folks in Copenhagen, which I really enjoyed visiting, even though I'm still not sure I'm pronouncing it correctly. So,
All right. Okay, so I'm just going to kind of dive in and talk a little bit about some of the things we're going to try to cover today. So first of all, these are some of the companies that we have worked with where the ideas that we're going to be talking about have been applied. So if you're kind of wondering, where our client base is, the companies in Europe, primarily Constellium is an aluminum company that's based in France. Sonian is a hearing aid manufacturer based in Amsterdam. Novozymes, of course, is the enzyme company that I mentioned earlier. Trimax and Gallagher are based in New Zealand. We've got a nice user community in New Zealand, and that in the United States. Probably the company that I've worked with the most is Keurig Dr. Pepper. They have fully adopted both Agile on the software side and my approach to Agile on the hardware side. And I will be sharing a little bit more about their story as we go on, because it's quite interesting one. So these are some of the people that are using some of the ideas we'll be talking about. So the first thing I'm going to share with you is why just use Agile doesn't work for physical products. And some of the challenges that occur when you take the practices that were developed for software, which is a very specific problem domain, and then you transfer those into the physical product space, which has very different conditions. And so we'll talk first about that. We'll talk about the 3 breakthroughs. The 3 breakthroughs actually happened in that project at Novo Nordisk that led to an effective approach to apply Agile principles in the hardware development space. We're going to talk about rapid learning cycles, which is the core of that idea, just kind of very briefly talking about using Agile in the early phases to accelerate hardware development in early development. Then Kathy's going to talk about integration trains. She's going to share some work that she did at HP during her time there that we're beginning to work and apply with a client of mine now to see if we can extract out the general principles that are making it work and develop some kind of more standard approach to it. And then we have outstanding questions. The things that for us are like, as we reflect on this, we're like, well, we don't actually know. So maybe you guys have some experience or maybe some thoughts on some of those outstanding questions. And then we'll end with a little bit of how to learn more, how to stay connected with us. All right, so starting in about 2015 or so, someone, I started getting these phone calls from people who had been following my work or who found my work. And they were calling me because the hardware teams were in trouble. And the reason why the hardware teams were in trouble is that someone had a very successful implementation of Agile in software. And they were telling the hardware teams, well, you guys should just use Agile. It's working so well for us. It's helping us, in so many ways. And we think that it would really help you too. So you should just use it. These are the kinds of problems that they reported. And there's definitely some patterns. First of all, most Agile methods require some kind of daily Scrum or daily stand-up meeting. It's a standard feature of most of the Agile methods that I've encountered. For a hardware team, those meetings are frustrating. And they're frustrating because a software developer makes progress every day. They make progress every day in implementing a user story. And a hardware developer, this is what a daily stand-up is like for them. Okay, you come in one day, what did I do? Well, what am I going to do? I'm going to set up that test. The next day, what did you do? I set up the test. What are you doing today? Well, the test is running. The next day, okay, that test is still running. And that may go on for a week or two or even longer. And so they don't have the same sense of making progress. They also don't have the ability necessarily to share work. So one of the things that happens in a software context with a daily stand-up is that you're able to switch work from one person to another. If one person's overloaded, another person can maybe pick up one of their other tasks. But you can't give a mechanical engineer the tasks that are on an electrical engineer that's in there, that's been assigned to an electrical engineer. You can't give an electrical engineer work that's been assigned to an industrial designer, and you would not want to, right? And I'm sure that if any of you work on firmware, you would not allow any of these people anywhere near your code. So we don't have that same benefit of being able to kind of switch work around and rebalance workloads. So it doesn't really even help the same way. Another major issue, done is really hard to define. So maybe this is an example. This is a wireless mouse, right? So what is this, just looking at just the runner that's along the back that allows it to, allows it to change from one surface to another. I have to use it to go backward, sorry. Go back, sorry about that. Okay, if I'm just looking at this, where is this done? Is it done when there's a CAD model? Is it done when I've located a supplier? Is it done when I've received the supplier and located the parts? Is it done when I have imported that, integrated that into the first system prototype? Is it done when it's in mass production? So the idea of what none means is a lot harder, and hardware teams can really twist themselves up into knots trying to figure out what that means. But aside from those kind of logistical challenges, there's some other fundamental problems. One is that even in order to make something like this, I've got a complex chain of dependencies that I have to manage in order to take something like this from a drawing and turn it into something that's in mass production. There's a lot of pieces that have to come together. And Agile methods primarily use backlog management. In fact, I've had hardware program managers that have been told, do not make a Gantt chart, when the only way they can keep track of those dependencies is in a detailed project schedule like that. So that's one issue. Another is that the Agile methods emphasis on demos will drive hardware people to try to demo stuff, which means they're building prototypes. And in the hardware space, the prototype is not the most useful way to learn. If I want to change the glass that's on top of this, my best way to learn about that glass is not to make these. My best way to learn about that glass is to get samples from different suppliers of different options for glass, and then subject those to different kinds of physical tests, all of which will look nothing like the final product. So I could demo that to a knowledgeable audience, and that would be helpful for them. But it's not the same. And Agile practices tend to drive teams to do things that are actually more wasteful than helpful. But the biggest challenge is this. The problems that arise when you're making something like this are problems with late design changes. The problems with loopbacks. The problems with when we actually added all the pieces together, it costs too much to make. And all of those problems are still present in a team that's using Agile or a hardware. It does not actually solve the problems that they have, okay? It solves the problems that software teams have, but it doesn't solve the problems that hardware teams have. And this is why. This is the life cycle of software products. These are the things that a software team has to do. They have an idea, they might build a proof of concept, then they'll do some design and coding, and they'll do alpha and beta tests, and they'll release to customers. And they'll probably do multiples of these. They'll probably do, even a series of customer releases, right? It does have to be installed. For most of us, that's as simple as, pushing the update button on their iPhone. and then they have to support it. All right. So these are the major activities. For a hardware team, it actually looks quite a bit different. For a hardware team, well, they're still doing things that are similar. They're still doing an idea, proof of concept. They're still doing detailed design. They're still making some prototypes. They might even have early use tests, like alpha beta tests, right? They're still, but to get to the product, it has to reach the customer's physical location, and a lot of other things have to happen ahead of that. It has to be sourced. It has to be put into a production process and produced. It has to get usually from some manufacturing base in Asia or Eastern Europe to the place where it's stored in finished good inventory. It has to go through its distribution channels. And so for a physical product, often one of the things that drives the date by which something needs to be done is when it has to be on the dock of one of your channel partners. Like in the US, Walmart is a big one. Okay, when does it have to be on the dock at Walmart? That's what determines when that product will be released, right? So all of these things have to happen. So I have a client, Gallagher, one of the companies on the list, that makes agricultural technology. Their products have a 25-year lifespan. That means that all of the decisions that they make at every point along the way, they are living with for 25 years, right? There's no ability to do an over-the-air update for the kinds of things they make. They make fencing, high-tech fences, right? So all these things mean that the problem that a hardware teams are dealing with are very different than the problems that a software team is dealing with. So that drives what we need to learn. On the software side, it's a lot about, will the customer like it? How long will it take to build? How will it interact with this environment? This is an iPhone 12. Will it interact differently with an iPhone, 11 or even an iPhone SE? What are the kinds of mistakes that we might make in the process and what kinds of mistakes might a user make, and how can we protect the users from those mistakes? In the physical product world, we have all those questions, but we also have questions like, is our idea physically possible? Marketing people are really good at coming up with ideas that violate the laws of physics, right? So what materials will we choose? A huge one in the physical space, can I make this in the quantities that I need to make it at a cost that will allow me to make money from it? Another big one, okay? How do we source it? How do we support it in the field? So these kinds of questions that are on under the physical product, these kind of questions, again, they have long-term consequences. Once I've chosen the glass that's going to go on top of this, we're going to order that glass. We're going to order a lot of it. We're going to integrate it into our manufacturing process in ways that will be difficult to change if we decide we don't like it. And then we have to figure out how we're going to support it. What happens if a user drops the mouse and it breaks? Is it going to create is it going to be dangerous for them? Okay, so these are all things that we have to think about. So we kind of summarize all this as saying that in general, and this is a big generality here, in general, in the software world, things have relatively low cost of change. If the software that's running this mouse, the software that I have on my computer, if that needs to change, I can get a message that says, please update your driver. I can get even a message that says, please update the firmware in the mouse. So there's a firmware update routine, right? So it can be changed. But on the other hand, once I've bought this, I've pretty much bought it. It's never going to be, they're not going to, replace this for me unless there's actually a serious safety issue, right? If it just doesn't work well physically, if the build quality is poor, then they're going to be facing some warranty costs, but I'm going to have to ship it back to them. Okay, so you think about the firmware, you think about the driver, those things have relatively low cost of change. It's not zero, it's still a hassle for me to change it, but it can be changed. On the hardware side, we have things that have a very high cost of change. So when you're operating in a low cost of change environment, what we want to do is we want to make a provisional decision. And then we just want to put that decision out there and see what reaction we get. So we design, the interface for the driver. We have users test that, and they'll throw it all over it. They'll tell us what they don't like about it, and that's fine because we'll just fix it, right? For the hardware kinds of problems, the high cost of change problems, what we want to do is we want to run experiments. And we want to run very targeted experiments, such as how strong is this glass? How formable is this glass? How well does it integrate into our manufacturing process? Then we'll make some prototypes, and then we'll use those to learn. And then of the available options for glass, we'll choose the glass, and we'll make a final decision. Okay, but we're going to make that decision after we've done a lot of experimentation, a lot of learning that may look absolutely nothing like the final product in order to do that. So go forward here. So I've summarized all of this in this graph, which basically says, when do you use what types of project management? Okay, so when I'm talking here about Agile project management, I'm talking about things like Scrum and SAFe that are methods that apply Agile principles to software development. That's what's down in that space. And the software development Agile methods are tailored for an environment where we have high cost of change, and we have low cost of change, and we have high uncertainty. Okay, so we have low cost of change, we have high uncertainty. Okay, that's the world that Agile software lives in. We also have traditional development. I don't use waterfall. I don't use waterfall because waterfall does not work anywhere. Waterfall doesn't work in hardware, it doesn't work in software, it doesn't work anywhere, okay? But the tools of traditional project management, things like Gantt charts and some of the risk management tools, some of the change management tools that are part of traditional product development, those things work much, much better in an environment where you have low uncertainty and you have high cost of change. So if you think about building a skyscraper, we know a lot about building skyscrapers, right? And at the same time, we also know that we have to lay the foundation, and the foundation has to be right. Because if we get the foundation wrong, it's going to be very expensive to fix it when there's 50 stories on top of it, right? And so we also know that we're going to build the first floor and the second floor and the third floor. And we know the sequence of activities that have to happen at each floor at each time, and we can make a very detailed schedule. And there will be things that change as unexpected things happen, like weather, or maybe one of the labor forces goes on strike, and we'll have to adjust the schedule. But in fact, the tools help us do that in that context. Okay, rapid learning cycles is intended to fill the gap where we have things that have very high uncertainty, but we also have a very high cost of change. When you're operating in that quadrant, the thing that we have to do is we have to improve the quality of our decisions, because those decisions are things we'll be living with for a very long time. And at the same time, we do leverage some of the Agile principles to help us manage the uncertainty, because that's one thing that Agile helps people do very, very well. It helps them manage uncertainty. Again, it just doesn't look at a practice level like the things that a software team will do. Okay. And then I had a question. Well, what is the informal, what are those informal tools? Well, if you have something that's very low cost of change and low uncertainty, so think about, going to visit a town for your summer holiday that you visited before, right? So you know what you like, you know where you want to stay, and if you want to change, it's relatively easy to change. Well, then you just need like a to-do list for that. You don't really need a whole Gantt chart. You don't really need the structures of Agile either. You can just do it in a very, very simple way. Okay. All right. So just a little bit about what's actually happening here. Okay, so what's actually happening here is that most hardware development programs are one long, slow learning cycle. Remember when I said in that early slide that Agile software does not actually solve the problems that hardware developers have? Well, this is the problem that hardware developers have, okay? Which is that our processes force us to make decisions sometimes in early product development that don't get validated until late in product development. That is the problem of waterfall development. That it's, if you tried to do software, you would see the same thing, okay? The difference is that in the software world, we remedy that by running very short cycles of complete development. Okay, so I will take a user story. I will fully flesh out that user story. I'll write the test for that user story. And then I will code that user story, run the test, make sure it works, and then I'll demo it to a customer. And I'll try to do that in the context of one iteration. Well, I already said that doesn't work very well in the hardware space. We have to think about a different way to cut that batch size down. And so what we actually do is we take the learning, and the learning is the thing that we cut down. And so we frame our learning as a series of rapid learning cycles. All right. So we learn as much as possible as early as possible, and we delay decisions to preserve flexibility. And when we do that, when learning becomes the thing that we focus our Agile lens on, and learning is the thing that we break up, where we break up the big batches into small batches, then we find that teams are able to make better decisions. And when they make better decisions, they don't have as many of those loopbacks. So to give you one example, SunPower is a company that I've worked with here in the US. They make solar energy panels. They recognized that their standard process would require them to define who the customers were relatively early in the process, but they realized they couldn't do that. They realized that they didn't actually know who their customers were, and so they just delayed that decision. What happened in the meantime was that the solar energy industry dramatically evolved. If they had been forced to choose at the beginning of their project, they probably would have aimed at utilities, big, large, massive solar energy installations. What they realized is that their product was much better suited for decentralized solar, rooftop solar, solar on homes, solar on commercial buildings. Okay, by delaying that decision, they avoided some major loopbacks because they would have been aiming their product at the wrong customer. Okay. So we summarize all this by saying that we pull learning forward to identify and remove obstacles. We push decisions later to preserve flexibility. That's kind of the summary of what's happening there. Rapid learning cycles itself evolved from Scrum. As I said earlier, the ask that we had was, can we use Scrum in advanced development? And we learned that, yeah, we could sort of, but it had to change a lot. There were some big changes around. First of all, recognizing that hardware has a much more constrained plan. By that, I mean, we have things that have to happen in certain orders. We don't have there's no product owner out there that can just say, here's what's most important for the business, do that first. No, we kind of have to deliver the whole thing. And it has to be done in, an order that makes sense based on the fact that we're aiming at a mass production process. So we don't have as much room to play. So the very first change we made, in fact, was to eliminate backlog planning and go back to using a time-based plan that would allow us to keep track of those dependencies. Another big difference is what happens at events. What's happening at events for the hardware teams that I work with is that they're reporting on what did I learn. So what did I learn? What am I going to learn? And this means that at those events, they're mostly focused on sharing knowledge. We call those learning cycle events. They're mostly focused on sharing knowledge. And they don't do a demo. They share knowledge in the way that's the best for them, which is that they have these very short reports that they write about the knowledge gaps that they've closed. They also don't spend as much time planning because their plan is much more constrained. So they can set up a plan at the beginning. They do adjust it at the end of every cycle to reflect what's happened, but the adjustments are much, much smaller than they would be on a software team. Okay. And then finally, and most importantly here, the unit of work here is the knowledge gap. So we do take and we say, okay, what does this team need to learn? We break it down into small pieces we call knowledge gaps, and those are the things that we manage. We intentionally do not call them user stories. I know that there are a lot of Agile for hardware advocates out there that do say that hardware teams should write user stories, but in my experience, hardware teams can really twist themselves up into knots trying to make their work fit into user stories. And all that really does is dilutes the power of user stories for the software developers who really need powerful user stories. So I prefer to just call it something else. Yep. Okay. So someone has a good question, and it says, building the thing right versus building the right thing. When you say learning, can you address both? And absolutely, yes. In fact, you kind of have to do it together. So let's say that I'm using a new kind of glass here, something that's never been done before. Well, there's a whole, like, is it the right glass that's going to help us fulfill some customer need in a way that's going to deliver a better product to them. But then we also have to figure out how to make it. And so, and they kind of go hand in hand, right? So we do have these things called learning cycle and integration events. They will, again, they happen on a regular cadence. When I have teams that are hardware and software working together, a learning cycle event will happen at the same time as a sprint event within a day or two of each other. And we'll have hardware team people come into the software events and vice versa. We just recognize that they're doing different things. All right, and then so this is kind of a summary of the three breakthroughs that led to rapid learning cycles. One is this idea of doing a time-based rolling wave plan instead of a backlog. And again, that's to address the dependencies and the resource constraints. The second is to focus on the knowledge gap as the unit of knowledge. They were originally called HIPs, hypotheses in progress, but most of my teams use knowledge gaps rather than a unit of work, okay? And then finally, really focusing on decision quality as the way to undo those long, slow loopbacks. Because the long, slow loopbacks in hardware are much more related to those decisions and not so much related to work that's been done. Okay. So when teams do that, these are the results that they report. These are the things that they tell us. I'm not going to read that to you. I will just let you read that for yourselves. But basically, what we found is that when we think about Agile, we go back to first principles and we apply Agile in this way, then teams are able to actually realize the benefits of Agile by doing it. So now all of that is talking about what happens in the early stages of product development, but what happens when teams start moving into the later phases of product development? What do they do then? And especially what do they do when they have to integrate with a software team? So that's where Kathy's work has been focusing recently. So I'm going to switch to that slide and then I'm going to give Kathy control.
All right. So as Katherine was describing, the rapid learning cycles are going on mostly in the early stages of the project. And so there's a frequent short cadence at that point with a lot of knowledge gaps, a lot of key decisions. And then as the design solidifies and a lot of the decisions are made, the knowledge gaps and key decisions are a lot fewer. The cadence might be less frequent. So the question becomes, yeah, we still have a lot of the project to go and an awful lot of work. Could this be more agile? What would that look like? So to look at that, I found it helpful to go back to the fundamentals. What is actually making Agile work? What is actually making rapid learning cycles work? What's the common things that are making both of them work? And then how could those be applied later in the project? So a big, I think, very fundamental common thing is the idea of these small batches, that you have small batches moving through the development process instead of one large batch. A waterfall project was basically one large batch, like 18 months long. You had to finish all the design before you could do any coding, at least in theory. And then you did all the coding, then you did all the testing. And the result was invariably when you got to the testing, there were a whole lot of surprises where you had to go back and rip apart stuff you'd already done and do it over. And it became very unpredictable as well. So the huge insight of Agile, I believe, was splitting it into small batches, and not just any batches, but very carefully defined batches that would deliver immediate value. They're delivering immediate value in a couple of ways. One is, yes, you have a feature you could show a customer, you can get feedback from the customer. You might, depending on your type of product, even be able to sell that by itself. But the other huge advantage is you're getting feedback on how long it takes to complete a piece of software. And truly, working software is the only valid measure of progress. because there is a huge amount of uncertainty, much more so than my hardware colleagues have, in how long it will take to do anything. And that was one of the big breakthroughs. For any of you who have lived through a waterfall to agile transition, you may have seen this, that you become able to predict when things will be finished much more accurately, and that can really be a game changer. So we have that going on in Agile, and in the knowledge, the rapid learning cycles, much the same Agile behavior of being able to predict when all of these knowledge gaps might be finished, of being able to define what exactly is a knowledge gap, how do I know when it's done, and having very specific formats and very specific criteria for both. They're not the same formats, they're not the same criteria, but they both have them. They're both delivering value, and they're both giving the project a lot more flexibility and a lot more control. So how can you take that concept and apply it later in the project? Basically, you're going out hunting for big batches. Where else are we seeing big batches with long, slow loopbacks? And as Katherine and I have been talking about this in the past months, realizing that one of the things I worked on extensively at Hewlett Packard the last few years I was there was actually a really good example. So I'm going to tell you a story about long, slow loopbacks in hardware software integration testing. One of the frequent things we see in mixed hardware software projects is everybody's delivering into an integration test, and the integration test itself is built as a long suite, weeks and weeks long sometimes, and at the end of it you get a bunch of defects, and by now it's quite a long time since the original user stories were delivered. So you've sort of broken your agility there. And typically we see the integration test planned in large chunks for a couple of reasons. One is that they're using physical prototypes, and the physical prototypes are expensive. There usually are very few of them, and so you're kind of economizing, optimizing around how many you have and trying to make the best use of them. It also often looks like integration testing would be easier if you lumped it together into large chunks. And sometimes it's simply that's the way things were being done. We've always done it that way. It might be a holdover from a waterfall method. And I actually see this on pure software projects as well as Agile projects. I've seen this in my consulting practice. Is the individual development teams are acting Agile and they're all delivering user stories, and then those are integrated together, and suddenly you find there's a big long integration test and it isn't visibly connected to the user stories. It's not really clear when the user stories started delivering. It's not real clear which user stories are related to which integration test, or how you would know when the user stories really finished, and you're not going to find any more defects. So you get long, slow loopbacks, and you don't have a lot of visibility into any particular user story's completion. It's one of the surprises when people first start Agile on a project of any size, is realizing that their story is not actually done when it's delivered to system test. It's done when it passes system test. So you end up with a system that's not acting Agile. And some years back, we had a team at HP that addressed this project and then later published some of the work so that I can share it with you. So I'm going to tell you that story. This is a story from inkjet printers. Inkjet printers are a fairly complicated system with sometimes hundreds of people working on a single project. So you have hardware development, you have electrical engineers, you have software engineers for the embedded software. You also have software engineers working on the drivers that go on your PC or your tablet or whatever. And you have cloud services that are doing things like offering to sell you more ink. So a bunch of different things that have to come together. And in the back in the past, these would be all individual teams in individual departments, each with their own development process, some doing Agile, maybe some not, and these long integration tests. So as the development teams individually started switching to Agile in the software world, they're having more and more trouble connecting what they were doing with the hardware or with the integration. And our manager challenged us to break up that integration testing. So saying it's a big batch, try making it smaller batches. Try to make it smaller batches by breaking it along system lines. Understand that what you're testing relates to the system. So describe it in terms of the system. What behavior do you see? What behavior would a user see? And it still needs to, it's still a test, so it still needs to deliver useful information about the state of the product, the maturity of the product. So we started trying to break up the tests into smaller chunks and center them around these features or behaviors, a lot like an epic in software development. And we found some things from Agile software development were applicable, like if you're going to break it into chunks, you're probably going to be able to use whip control. You're probably going to be able to use cadence. A burn-up chart might make some sense. But some things didn't really make sense, like the whole idea of a backlog for exactly the same reasons Katherine was describing. There are a lot of dependencies between things when you're doing a major system integration, and there is some ordering. It can't all be done in any random order. And the other huge difference was that these chunks typically were not individually releasable or shippable. So that's clearer if I show an example. And this is from the original paper, the chunks that were being used at that time. And it starts out with the minimum chunk. So the minimum printer chunk was a test of the printer all by its lonesome little self, plugged into the wall, so it's got electricity, press some buttons on the front and get a test page. So definitely not something anybody would buy. Why would you want a printer that can't do anything but print a test page? But from a system development point of view, that being able to print a page was a very significant milestone, because that demonstrated your paper pull mechanism was working, your mechanisms for putting ink on paper were working, your ability to align the ink or align the, not to get technical, but align the things that are putting the ink on the paper so you get nice, straight, crisp lines. You're getting good, correct color. That is a whole lot of things come together to make that minimum printer slice or chunk. Then the next few chunks were gradually bringing in additional subsystems. Now that we know we can put ink on paper correctly, we'll bring in the ability to connect this to a PC and send a job from a printing program into the printer. So a whole bunch more stuff has to happen, and you get a page from Microsoft Word or whatever spitting out of your printer. So I gradually added several more framework chunks that built up more of the system, and then additional features. Can we use, and yep, that one's coming up. So so we built the real features and tested real features. And what these look like, if you looked inside one of those test chunks and looked at the actual test definition, you found it looking an awful lot like a user story or an epic. It started with literally a statement, as a user, I would like to print these size photos. That was the goal for that integration test chunk. And it had some acceptance criteria, which were being called customer satisfiers. And it had some specific things that you could do or were supposed to be able to do. So it's as a high level feature, it's got a bunch of detail attached to it. You started being able to see when the user stories would connect, which user stories from a software point of view, which were at a very detailed point of view, when did those need to be done in order to do this integration test chunk? So you started to have connection between the integration testing and the individual software stories at a much more powerful level. So we're building these by doing thin slices through the system. This picture is from a book written by some of my colleagues in the LaserJet division a couple of years after the slide that I just showed. And they were showing how they were developing firmware in a very iterative manner that fed into this integration testing train system. And you see here slices going through the software. And at first, there's a slice that's just doing software with, yes, some emulator, which is actually could be another piece of software, or it could be a specially designed piece of hardware to like substitute for a whole printer. And gradually you bring in the pieces. So they're not shippable in terms of anything a customer would want. Like they do not buy firmware because they like firmware, but it provided valuable learning. So in that sense, they were delivering value, and that was the value that we were defining these batches to have. So each batch has to deliver value. The value was being able to establish that we had working pieces of the product and sticking as much as we could to a customer point of view, but admitting that sometimes what you need to know is if your architecture works. So this slice picture, I've seen this very similar picture in a number of different Agile software books. Some authors refer to this early slices as slicing through a layer cake. Some of them refer to it as building a walking skeleton, so that you can see that everything talks to each other, but it doesn't actually do anything yet. So those are our chunks, and we often refer to them as slices or slivers. And we found that once we had them defined this way, we could start mapping the user stories. So that made it possible to connect the planning across the individual teams and the whole integration team. So we discovered a number of characteristics that the batches had to have. And now that I reflect on that later, having also worked on rapid learning cycles, which didn't actually exist yet at the time these original papers were written, we see that the batches we were using had characteristics of Agile software batches and some characteristics of rapid learning cycles batches. So it was similar to Agile in that each batch was a real chunk of functionality with actual business value, and it was from a customer point of view, and we were bringing in as many layers as we could, and it had very specific acceptance or pass criteria. It was similar to Agile development in that it was answering useful questions about the product for at least one team, but preferably for multiple teams. And sometimes it took a little explaining that, does this work, is actually a useful question. People want to know the answer to that. So the integration test chunks or slices were defined to answer useful questions. And once you realized they were answering questions, you realized you could prioritize questions that involved more risk and do those maybe earlier than some of the ones that were lower risk. So after doing a couple of projects with these slices or slivers, we ran across Dean Leffingwell's work with the Scaled Agile framework. And in reading that, realized that the Agile release train concept could apply here also. I think what we were doing was not actually an Agile release train in the way that SAFe uses it, but there's some strong similarities. So you can call it an integration train. And the key concept there was this fixed schedule where the train comes by and you get on it, and if you're not on it, you have to wait for the next train. So how that plays out with an integration project is you've got all these teams that are trying to feed things in to deliver slices. You've got a bunch of different slices you're going to test in a couple-week period. So you set up a cadence and say, Monday, we start testing all the slices that have been delivered. If something hasn't been delivered, then it waits for the next train. And this sounds simple, but it's amazing how much it helps in that it cuts out all of the discussions about, oh, should we delay the start of the testing until Tuesday to allow so-and-so to get their one last slice on, and then how much do we move this out? And there's actually a lot of time being spent on those discussions, which you stop having them, you can use that time to do development, to do testing, to actually make product. And so it was very powerful. And today, how I would describe an integration train is roughly you would plan slices or chunks or whatever you're calling them for each train. Rolling wave planning will probably work better than a backlog. So have a like overall plan and choose a few train stops ahead to watch and see what's going to come or what you would like to have at each of those stops. And when the train stops and it's, you get your hardware prototypes, your software builds, your test harnesses, and you start doing the testing. Once you start doing the testing, you do not add new slices. So no more new features. So exactly the same as a sprint. You don't add more user stories in the middle of a sprint. You don't add more slices in the middle of a train. However, you do add sometimes additional software builds because something is broken and you need the bug fix. So you can accept additional builds if you have to. And the goal for each train is to test all the slices and be able to have all the slices pass and declare them done. So the idea of done for a slice means all the tests passed, we're happy, we don't have to go back and redo any of the development work underlying this. Once you realize there's a concept of done associated with a slice, then you can start tracking the slices. And our manager suggested using this burn-up chart or cumulative flow diagram to track what we were doing. So this is one of the very early projects. And the yellow is things that are actively being developed. The green were things that were in system test, in integration test. And the dark green are things that have passed. So those are all slices that have passed. So you can draw how many chunks or slices do we plan to do all together. And you can see this project's already had some scope creep. And then when's our release date? And from the time we started system test, how if we do and we have this many slices to do, what's the average rate at which we have to accomplish those? All you have to do is draw lines. Like if we can't stay more or less on that line, we're not going to meet the release date. So you can see this project started out on that line, and by a couple of weeks in, its average is slacking off. And what I found over time working with these cumulative flow diagrams was that it took 3 or 4 weeks to accumulate enough data to get a good extrapolation. And then after that, if you had 3 or 4 weeks in a row that were showing the same pattern, that was probably going to be the pattern until some process change was made. And that took a little while to convince people that if you see that happening, it's going to probably stay on that line until you do something different. So if you don't like that line, you've got to think about what you do that's different. One of the questions on this one was, should we be trying to develop faster? And actually, you can look at how fast are things entering system test. They're going into system test plenty fast enough. They're not coming out of system test fast enough. So what's going on there? Are they not being tested fast enough, or are they not passing the tests? So it doesn't take very long to figure out what's going on. And that turned out to be quite helpful. You can also see this project didn't start system testing until pretty late, and that definitely was something that could be improved upon, and was. So the overall practice of the integration train, I think, is a way to tie together hardware and software development. And I don't know that the train analogy is exactly working in as well as it could in this situation, but the things that are being done, the breaking things up into small chunks that have value, having a very clear definition of what the chunk needs to look like, format, criteria for being finished, what does done mean, that has to be user focused, that all works. Having a train style cadence to bring things in together so that you're not constantly interrupting yourself with late arriving development, that also worked really well. So you can make an overall plan that shows the goals for the train, and the goals are driven by the integration needs of this overall system. So an awful lot of the goals do look like we need to pass these tests. Why do we need to pass these tests? Because they're describing basic features that we have to have. So it's pass the test. But having the test defined in a way that linked to the user behavior and linked to the user stories allows each discipline to plan what they need to do to meet the goal of the train. And the Agile teams typically have epics, user stories, a backlog. The hardware teams more likely have prototype build objectives and more likely have a more time-based plan and are not using a backlog. In the integration planning, I recommend using rolling wave planning rather than a backlog because, again, there's a lot of interdependencies and you need to be able to see those. So you do a high-level plan at a 50,000 foot level that goes over the whole length of the project, and you just see some major events or checkpoints maybe, and maybe some major integration points, and then do a complete list of which slices or chunks you're going to use or you want to test for just the next couple of trains. And that would be analogous to just planning the next few sprints. And you need a little bit further of a look ahead than on a classic Agile, a pure Agile software project, just because of the amount of dependencies. And then you need a team that's working this. So you need a cross-functional team of technical people. So hardware architect, software architect, test architect, people who can make technical decisions, getting together on a regular cadence to say, are we going to have the stuff for the slice pulled together? If not, what do we need to do? Can we pull in another slice and have that one done earlier? What do I need you to do so that I can finish my slice? Hey, software, could you build us a test harness so we can do this particular piece of hardware testing? You get discussions like that going on in train planning meetings. So that was very, very powerful. So we have a question here about the red and blue in the previous chart. The red and blue were planning stages. One of them was actually backlog grooming, if I remember correctly. It's described in the paper, so which we have the references for at the end here. So we've talked about the rapid learning cycles and talked about integration train. And there may be other large batches lurking in hardware development. We don't really know at this point. So we have some questions, and I think I'll turn it back to Katherine here.
Yeah,
we're thinking about.
Yeah. So one of the in the chat is in the book, is there a chapter to cover a modified version of the Agile Manifesto and the 12 principles for software? Well, I've actually been writing an article series on exactly that. And in another couple of slides, when we talk about how to get in contact with us, you'll see that I've got a blog called High Velocity Innovation, and in that High Velocity Innovation, there's a series of articles on Agile for physical products, and that is this article series I'm in right now. I just finished and published principle number 9, and I'm just like remembering. When you write an article series like this, sometimes you don't always remember exactly what that one was. That one was on, technical excellence, accelerating innovation. So basically looking at how the technical excellence affects, and how that drives agility, which is true for both hardware and software. But again, it looks differently. I will share the URL to that on a slide. And what I'm going to do right now is I'm going to do this for everyone. Is I'm going to upload a PDF of these slides. And this PDF has all of the links that I'm talking about. So it has all of the links to everything that I have shared with you. So let me just get that right now while I'm thinking of it and get that in there. These are the outstanding questions that we have around, around this process that we're still exploring. So is there a bridge between the knowledge gap on one side? or maybe the key decision maybe on one side and the integration slice on the other side for hardware that makes sense. Like, so, you know, in other words, is there a way to kind of divide up the work that's actually being done at a task level in hardware in a way that makes sense? That is something that would be a challenge. If you know, if they are making good decisions at the last responsible moment, which is a key thing that's happening in rapid learning cycles, you know, is there a need for them to do that? One of the things that I talk to my clients about with rapid learning cycles is that it helps you move from the area of high uncertainty to an area where you have high certainty. And remember, I have traditional product management over in the high certainty zone, right? So if we use rapid learning cycles to reduce uncertainty, do we, you know, does it even make sense? That's a question we have. Hardware teams use methods and tools like FMEA, which stands for Failure Modes and Effects Analysis, DFM, Design for Manufacturability Analysis. Those are important practices. Design reviews are an important practice in hardware development for error proofing. How do all of those things factor in to an agile process for hardware? Maybe as part of an integration train. How do we integrate sourcing, which for some of my customers, to be honest, is like the big thing that they do. They don't actually make much of what they sell. They mostly buy it from other people. Tooling, tool design, production process design. How do those things fit into this process? Most of these people see iterative development as waste. They don't want it. They don't even want to look at it until it's completely done. I have had people from procurement or purchasing tell me, don't bother to show me an incomplete drawing. Don't set up the system so that I have to look at it. I'm not going to look at it. I don't want to see it till it's done. Well, what does that do for, you know, how do you incorporate suppliers into the process? That's a huge, huge question. And then finally, there are a lot of people out there saying, well, you know, 3D printing is going to allow hardware developers to be more agile. And 3D printing does allow hardware developers to learn faster, but it can also help them create just a lot more waste, a lot more plastic to be recycled if they're not actually learning from it effectively. And so, you know, how can we use tools like this to enable a process that actually helps improve hardware development instead of just accelerating the wasteful things that they're already doing? So this is kind of where I'm just going to go ahead and go to the next couple of slides just to show you what's in the slides. These are in your packet, so I'm not going to spend a lot of time on them, but then I'm hoping that we can open up these questions for discussion. So basically, sorry, wrong direction here. This is a slide that's in your packet about how to learn more and stay engaged. It has contact information for both me and Kathy, and it has a link to the paper that Kathy drew some images from. And then if you want to learn more about rapid learning cycles specifically, we have a class. It's an online program, a short 4-hour thing on the elements of rapid learning cycles. And I've given you a promo code if you would like to sign up for that. So that is what is in that slide packet if you download that from the chat. And with that, I'm going to go back to this and we're going to start taking questions. So if you, at this point, if you want to unmute yourself, David, I understand about 15 minutes. Is that how much time we have for this?
That's what we had planned, yes. However, if people can stay longer, they can, but yeah, we had planned it.
Okay. So just kind of looking at, so if somebody asked, how do you be a reviewer for the book? If you go to the High Velocity Innovation link in your packet, you can sign up to the Agile for Hardware series. That's where we're going to publish the material. That's where those chapters will be posted. So we would love to have you. We'd love to have reviewers. I'd love to have engagement with you. So that would be the best way to do it. Clients that have portfolios of hardware programs that have applied rapid learning cycles for portfolios or apply it to innovative product development or existing well-established. And I'm going to answer those together because they're kind of the same thing. And that is that most established companies learn pretty quickly that if they want to release multiple products, they have to manage a portfolio of products. And where and how we apply rapid learning cycles is we apply rapid learning cycles to the process of qualifying an idea for the portfolio and making that an expectation so that the portfolio managers can make better decisions about which dimensions of the portfolio we'll take into the next phase. And so a well-organized innovation process is, as you probably know, an escalating series of hurdles. So in an early phase would be very, very fast, just a very, very quick investigation, sometimes just three learning cycles long, just to very quickly investigate an idea. In the next phase, they might get a little bit more time. They might get 3 months to investigate. Then in the next phase, they might get a little bit longer. And at each point, the hurdle to get from one phase to another is higher. And rapid learning cycles are how you get from one hurdle to another until you get into the more execution-focused phases of development. And so that's how they're using rapid learning cycles in a portfolio management context, and also how they're using it to help identify innovations. For existing products, it looks a little different. So one of my, so I've worked with a lot of consumer products companies, and consumer products companies often have roadmaps. And so what they might do is they might use rapid learning cycles around features, and they might not know exactly when a feature will be targeted for a product, but they'll use rapid learning cycles to mature the feature. And then when the feature is ready, then they'll pull it into their product line. So that's something we've seen a lot. Simon, I've seen the culture of do many things at once, want to solve the whole problem at once. Some engineers want to solve the whole problem, tend to be less than ideal. So Simon, could you come on and say more about that? That's a very interesting comment. Are you here?
I am here. Can you hear me?
Yes, I can.
That's good. I pressed return a bit early. What I was trying to say was I have met exactly what you described, which is hardware engineers who are given a problem domain, and they want to change 40 things at once, all at once, and then the whole concept shifts 180 degrees a week later when you next speak to them. And I can see your idea of let's collate batches of knowledge as being sort of the iterative elements. That makes sense in a lot of ways. What I was more intrigued about is the exact same people, the human element of this conversation, tend to also be very bad when you come back to them later and say, well, you've learned all this stuff and you've made today's series of choices, that's good. They always seem very bad at helping you plan the integration phase, for want of a better phrase, because they're always thinking in the whole. They're trying to solve an element of it, and if they move one element, the cascade effect in their mind and in the design keeps moving. What's your experience of that?
I'll just say that's very much reality.
It is, yeah.
Is that, yeah, their systems are so tightly integrated that if they change one thing, it impacts everything else. Yes. Right. And so one of the things that I really work to coach teams to do is to think about this. I'll coach them to look for the NUDs, new, unique, difficult. So what's new about this? What have we never done before? What's unique about this? What has no one ever done before? What is difficult? What's just inherently hard about doing this, right? And then to look within there for the decisions that they're going to make around those things. And then to try to pull the learning forward in a way that's disconnected from the product. So that's why, in fact, it's one of the reasons why demos actually can cause hardware teams problems, because a lot of times what I need to know in order to make a design decision, say about what material to make a component out of, my best experiments are going to look nothing like the final product. That is, and if I understand what I need to know in order to make that decision, and then I design my learning around what I need to know, then when I design the component, it's more likely to work. And I'm not as likely to need to make a change to it after it's been put into this finely tuned system, where if I have to change it, all of a sudden it changes everything else around it. So that's what we do, is we recognize that things like that are the very definition of a high cost of change decision. So I want to pull all my learning ahead of that as much as I can. And then so that when I do make that decision, it doesn't have to change. Does that help?
It's certainly relevant. I think the hard thing is that, as you correctly identified, many hardware choices have masses of interdependencies, and if nothing else, the traditional way of designing hardware is very sort of a man in the corner thinks up the solution. There's normally 1 hardware engineer to 5 software engineers sort of ratio. These are just reality facts. The only thing I've seen that makes a sort of a difference to that conversation is depending on the amount of simulation automation type tools that can be used in the hardware world. The more you tend to have those, the more rapid the learning can be. It seems to make a difference to those sort of avoiding those types of problems.
Yeah, because what those tools allow them to do is to accelerate their learning, and to accelerate their learning in ways that don't, especially modeling tools allow them to try lots of different things without having to actually cut parts.
Yeah.
That can make their thinking a lot faster. But but one of the key shifts that people make when they start using rapid learning cycles is, instead of thinking about, I have to design this component, what's the design for this component, and then doing build test fix cycles to get the component right. It's instead to say, well, what do I need to know before I even make the design that would help me make a better design? And then what do I need to learn? How can I learn that? Right. So when I'm working with hardware teams, a lot of the work I'm doing with them from a coaching perspective is helping them make that particular shift, because it does make them a lot more effective.
Okay.
Yeah.
I'll stop there, David.
Okay. All right. So could you elaborate more on how to handle stakeholder feedback at the early stages of development? When we're using rapid learning cycles, we're engaging with stakeholders at the level of key decisions. So key decision is a high impact, high unknown decision that usually requires stakeholder input to make. And the team has broken that key decision down into knowledge gaps and gone off and closed the knowledge gaps. So, like I said with this, the glass that's going to go on the cover of this, that might be flagged as a key decision. It might require input from sourcing, from finance if there's a cost implication, from the user experience team for sure, from marketing maybe. And so a lot of people care about what this thing looks like, right? But and then what the team presents is based on the knowledge that we've built around this, this is our best recommendation of the way to go. And then the stakeholders discuss that decision. Yeah, you've chosen the most expensive option, but I think we need to go with option number 2. It doesn't look quite as good, but then the industrial design people say, yeah, but that's going to really hurt, our shelf, the way we look on the shelf compared to our competitors, and so they'll have a discussion around that. And that's what we find is the most valuable way to engage with stakeholders, is really to get them engaged around these high impact, high unknown decisions. As a way to help manage that. So Renato, was that responsive to your question? Okay. And then Brianna, you had a question?
I do. Sorry, I just admit now. It was, thanks for the answer.
Okay, go ahead, Brianna.
Okay, so I actually have a question. I'm going to ask it badly, and then I'm going to tell a story and then re-ask the question, because I'm going to do a disastrous job of trying to articulate this. Did you ever have products where you had no actual rapid learning cycles once it was in use? And the reason I asked this is 2 jobs ago, I worked in oil and gas, and I built drilling controls for blowout preventers for offshore deep water rigs. And one of the components on the drilling controls is called a dead man auto shear. And you can think of it as like an emergency backup system. But this is a piece you can't actually test. You only know if it works if your rig doesn't blow up. And get it, you have a BP Macondo situation. And you can do a lot of, and the control systems have mechanical parts, electrical and software, and they're all built in parallel. But the thing is, you don't actually know if some stuff's going to work until your rig fails. And you have a BP situation, and some of these components, because it's so, the constraints around constraint manufacturing are so high, like the labor costs are so high, and the components are, the cost of them are so high, even assembly, even when it gets onto a rig and stuff like that, that you never ever really want to take them out of production unless you absolutely have to. So it's really hard to get feedback. And I was just wondering if you ever came into products where you never really actually, or built any products that you never actually had feedback cycles, and it was purely based on assumption, or best testing you could possibly do.
Yeah, so I'm actually working with a company right now named Keros Power. Keros Power is making a next generation nuclear power generation system. And they actually have this problem all over the place with a lot of their safety systems. It's like, even in small scale, they never want their systems to fail, right? And so I can tell you that the approach that we're taking on that is basically a lot of modeling in the virtual space, where you can actually blow up the reactor virtually and see what happens, and a lot of physical modeling where, at smaller scale, under controlled conditions, to try to get at that. But you're absolutely right. In that environment, the whole idea of understanding what you don't know that you know that you don't know, and what you don't know that you don't know, and then taking a risk-based approach to figuring out what experiments you need to run to build that knowledge as closely as you can, is really, really important in that space.
Yeah, thank you.
Yeah. So, okay. All right, and then I have another question from practice. How long % completion in project duration do you apply RLCs? And I'm going to answer a slightly different question. Which is that what I think about is, I think about it in terms of how much outstanding knowledge, or how much outstanding risk there is in a program. And so for a program that's an existing product, where you're basically just adding a new feature or two, and there's some new hardware parts, but a lot of the hardware parts are being reused, and there's a lot of a lot of stuff that's just known about it, so it just doesn't have as much unknowns. You might only use rapid learning cycles just a little in the beginning, just to get things going. But you'd still probably need quite a bit of the integration training, because you're still going to need to do the integration with hardware, software. You're still going to benefit from breaking up a lot of that testing. If you're doing something that's new to the world, like this nuclear power reactor that I was talking about, they're going to be using rapid learning cycles, or that kind of construct, all the way to the end, because there's always going to be stuff that they're learning. They're going to have a lot of new information come in. They're going to have a lot of risk that they're going to want to burn down, and as they get closer, they'll have more and better ways to eliminate that risk. And they can use the rapid learning cycle structure to do that. So they might use rapid learning cycles the entire way. I would say that most programs transition away from rapid learning cycles when they feel like their design is complete enough, and they begin to get close to tool release. And sometimes they'll use rapid learning cycles on the tools themselves. But if it's really more the but if you're in a world where you're basically making injection molded plastic parts, well, that's something that's very well understood. And then sourcing components that you can validate, and that's very well understood. Then most groups don't use rapid learning cycles once they've figured out what the product is. All right. Yeah. Other questions or thoughts? Space for risk management, risk assessment. Absolutely. This is all about risk. A lot of what's happening, a knowledge gap is that's not closed is a risk, but at least you know the risk you're taking. A lot of teams, this is going to drive teams to think about risk completely differently, because if they can learn what they need to learn ahead of making the decisions, then they can eliminate a lot of that risk. That really, really helps. All right. Okay. All right. So David, you want to say some closing words?
Yeah, so it's like we've answered all the questions and we're bang on time. How amazing is that? I guess we estimated the session very well. So thanks, Katherine. Kathy, that was a great session. I have lots of questions too, but we are out of time. But it was great to have you here. So thanks very much again for being here, for sharing your knowledge and expertise in this. That was really great. And thanks for everybody who came and asked all those wonderful questions. I think we all learned a lot. And please connect on LinkedIn, right? Katherine and Kathy, you can.
The good thing about Kathy, both Kathy and I, is that we're unique on LinkedIn. I am the only Katherine Radeka. I think there's another Kathy Iberle, but only one and not in Vancouver. So we're really easy to find there.
Awesome. So yeah, people, please do that if you want to ask more questions or link or connect to people. That'd be awesome. So yeah, thanks very much. Have a good evening or afternoon, wherever you are in the world. it was great to have you here. So yeah, have a good one. Thank you for coming.
Thank you very much.
Thank you. All right. Bye-bye.
Good evening. Bye-bye.
Thank you.